Next we do is calculate the area of convergence. That's a two-dimensional area on our surface. If we draw a line through the long axis of several stains where all these lines will meet, they should converge in an area somewhere in the center here. What I want to do is pick several stains that are elliptical from different sides of the pattern. We're looking at this to solve where this blood came from. I'm going to start with this stain here, and I'm going to line up so that I'm drawing a line through the long axis of my stain. So this is where the tail is going to help me out to figure out the directionality, but also to line up my ruler. And then sometimes what we'll do is just kind of show for a jury an arrow the direction that stain was going. So then I'll move around the pattern from different sides of it and draw through different stains. So this isn't done at every crime scene, but when we have a pattern like this, we have elliptical stains along the outside, and we have some circular stains towards the inside. This is the perfect opportunity for us to do some analysis. I could keep going and draw more lines through more stains, and it should all be coming back to the same general direction. So if this was on the wall and this was very low, this could be very powerful evidence to show that, that was low to the ground where this impact happened. Since we identified different stains that are striking our surface at different angles, we're gonna figure out the angle of impact that these stains hit our surface. We do that by measuring the length of the stain, we divide it into the width of the stain, and the arc sine of that number will give us our angle of impact. So we're measuring stains, we always want to use millimeters, allows us for smaller measurements. So what we could also use is a digital caliper, and that will give us precise sub-millimeter measurements. So I want to measure the length of the stain, the long axis of the stain. So this is 3.1 millimeters. And then I'd measure the width of it. So I'm measuring the widest part of the stain. That's 1.7 millimeters. We're going to divide 3.1 into 1.7. So if we do the arc sine of that number, that will give us the angle of impact, which is 33.25. If you had a regular ruler, you would just have to round up to the closest millimeter. So in this case, this stain is 4 millimeters. And then we measure the width of it. It is 2 millimeters. So we would divide 4 into 2, which gives us 0.5. And the arc sine of 0.5 is 30 degrees. And we can see it's basically at the same distance from our center, but just on the other side. If we look at this two-dimensionally, we know that these lines of our area of convergence meet here. But if I want to think about it three-dimensionally, that my blood is coming from somewhere above it here. So the next step will be is that we're going to calculate the area of origin. If it's coming in at a right angle here, I have a triangle. So this will be my adjacent side of the triangle. I know that it's 90 degrees from here. So that's my right triangle. And then this side that the path takes is the hypotenuse of the triangle. And so if I know the distance from my stain to my area of convergence, and I want to figure out how far away my area of origin is here in space, if I do the tangent of that, I could figure out the side, like SOHCAHTOA. When we analyze bloodstains in the field, I always feel it's better to do all these methods. We should be coming up with similar results, but if you messed up somewhere, one of those is going to be correct.